All right, now this is just going to be a very quick review of centripetal force, centripetal acceleration. And, I recommend that you just go over all the examples that you have written down in my note sheets that I've given you. So anytime you have a velocity vector and a force vector that's perpendicular, you're going to be going in a circle. Okay, and that's the actual observed acceleration of this object is going to be centripetal force. So that's AC just equaling v squared over r. Okay, so that is pretty obvious there what's going to be happening there. And of course, if I've got force centripetal, that's going to equal mv squared over r. Now again, I recommend you looking over all the examples. I'm certainly not going to cover all those in this video here. I'm not trying to make the videos too extremely long for you there, okay? But within the context of this chapter, though, we did cover one specific example about gravity. So what if I have a satellite going around the Earth? Well, we know there's not a big long chain keeping it there, so that we know that force gravity is definitely causing the force centripetal this time. Okay, but this is Newtonian gravity. Okay, so remember that the force between any two objects can be measured by force gravity equals the big G, m1, m2, and that'll be divided by r squared. So this is even true. Let's say I've got two objects, this object here and this object here. So if I double the distance between those, the radius squared tells me that the force of gravity should go down by 4 times. Okay, if I triple the distance between them, the force of gravity should go down by 9 times because over the radius squared. But if I double a mass, because those are linear, the force of gravity will only be twice that. Okay, so we can look at this just with two objects in general. Okay, but what about our satellite going around the Earth? Okay, so we have to remember that we have to calculate the radius all the way out to that satellite. 6,400 kilometers of that radius is going to be the Earth, plus whatever height you are above. Okay, and that's going to be just known as the radius that's going on here. Now I can find the force of gravity acting on that just using this equation. Remember, G is 6.67 times 10 to the minus 11. It's kind of small there. Okay, but if we take a look at that, I mean, I can just look at this and figure the orbital speed. So I'm going to go mv squared over r. Okay, and that's the little m is going to be for the satellite. Trying to make that look like a square there. That's a square. Equals my force of gravity, which is g little m, and then this is going to be big M, the mass of the Earth, over the radius squared. Solving for velocity, rearranging the equation, I do get the square root of big G, okay, big M over R. Okay. All right. Now, while we're on the topic of gravity, remember Kepler's laws. Okay. As planets go around the sun, 3 laws. The first one is they're elliptical. So Kepler's first law is that they're elliptical orbits as they go around the sun. The second was equal areas sweep out equal areas, okay, for the planets, period. Okay, so what does that mean? So if I have an orbit around the sun, I'm just going to put a little X for the sun here. And let's say I've got a planet here at this moment, and the next moment it's over here. Let me change colors here. So I draw a line to each of the orbits, so locations, and I just map out that area there. Okay, what if I am now, my planet is here, and then it'll probably be over here. Okay, I know this doesn't look really great, but there's equal area here that equals this here. So that means it has to be going faster here. Okay, we're slower as we're farther away from the sun, and we're faster when we're closer. And the third one is the orbital period is proportional to the cube of the radius, and that's this equation. T squared, the period squared, equals 4 pi squared okay, over, and then this is going to be r cubed, okay, over big G and over big M. Big M is going to be the mass of the sun or the star that the planets are going around. Okay, so that's just a quick review, okay, of that. Now, one last topic to cover. So to get a satellite up here from the Earth, we need to give it both kinetic energy and gravitational potential energy. Well, we're used to just mgh if we're close to the Earth. But I do want to give you a reminder, gravitational potential energy, when you're farther from the Earth, okay, is given by this equation. I'll write it under here. It's minus big G, a little m, and then of course big M being the planet, okay, divided by R. And remember, the only true place for gravitational potential energy to be zero then is infinitely far away. So if I put a 0 in for my radius here, I'm infinitely far away from my planet. That's where gravitational potential energy is going to be 0. Okay, so if I'm at the surface of the Earth, okay, I will then have gravitational potential energy equal to G m little m big M divided by R. And then if I'm farther away, I'm going to recalculate that as big G little m big M over my new radius, and I'll take the difference between those two to get my change in potential energy. Now remember, if I'm going around, I do have kinetic energy because I have orbital, okay, velocity. All right, now this one here is for my Mechanics C students only. So what if I have a planet here, okay, and we have, of course, some radius r, okay, but we have a density function sub r in this. This is the letter r here. Now let's say that equals b sub r. Now we just have to remember that we need to get mass. Mass, okay, is going to be the integral, okay, from 0 to r, okay, and I'm going to put an equal sign here, and I'm integrating then, okay, so we have to remember that rho is a rho sub r, and that does equal mass per volume. Okay, so then dm is going to equal rho sub r, okay, times dv. Okay, so then rho sub r, I got to actually put in br because my rho is a function of r. So then I'll have br. Okay, and dv is 4 pi r squared, little r. Notice how that's little r, okay, times dr. So then, of course, I'm going to integrate this to get my mass. And when I'm done with that, I will plug that mass value into my equation, force gravity equals big G, little m. Now, big M, I should have made that like a big M over r squared. So once I take that integral, I'm going to put that in here. And then I'll have a function wherever I'm at inside this planet. Okay, I will have a function for the gravity force acting on that object. Now remember, once I get out, if I'm out here, I'm just using G m big M over r squared, and r is the distance from here out, okay, to there. You know, and I agreed in class that we would, when we're in the planet, that we would make this a little r squared, right? Okay, and then when I'm out of the planet, I make that big r squared, because we have to remember that this 0 to r is the while I'm traveling inside the planet. Okay, and that is our centripetal and gravity stuff.